Well, good afternoon or good morning, wherever in the world you may find yourselves. I'm going to talk a little bit about LISP and why we chose that as the protocol to enable SD access, and why I believe it's actually what could be the protocol of choice for many software-defined networks in general. So I've been working on LISP for a very long time. My involvement with the protocol goes back to the original meetings at the IESG, and that was when I was focused on data centers. So we've been using it for a variety of applications, and I think what I'm going to share today is basically a distillation of what we found over time are some of the main advantages that we see for a software-defined network. So we'll talk a little bit about overlay networks and the role of the control plane in overlay networks and how LISP plays there. We'll introduce the foundation of LISP so that we level set. And then we'll go into how we deliver mobility at very high scale and very high performance. I'm also going to talk about how we've extended the protocol to deliver all the functions in one stack without having to change operations. So you'll find that you can deliver most of what you need in your networks today without adding different protocols or different types of machinery. So it all follows one simple principle, and you can get many of the things that you need today. So when we look at networks today, the leitmotif is that the number of endpoints that are connected is growing exponentially, whether it be IoT, mobility, or just connectivity in general. The endpoints are mobile, and we have a keen inclination to segment the network so that we take this whole environment where you have created basically an ideal attack surface and put it into different chunks so that if you are compromised, you limit the stretch of that compromise. Now, in order to deliver these networks, traditionally we've had a stack of protocols that we combine and mix and match. And if you've ever tried to build these networks, you know how complicated it is to combine even just simple spanning tree with first hop gateway protocols and then putting that into an IP network. And God forbid you have to add multicast to that and go ahead and segment it. And it keeps growing, right? So, so the idea here is that we want to cater for the very large scale of endpoints. We want to cater for mobility in a way that hasn't been done before. And we want to do that at a very high performance. Right? And we'll talk about the compound effect of the scale and the move of these devices. And we want to do all of this in a consolidated stack. So rather than having 20 protocols to deliver 3 or 4 functions, really, could we have one protocol stack and actually deliver all of these and extend it so that we can keep growing what we do there? So that's the implication of what the environment is posing as far as requirements, right? And we have taken a tack in terms of the delivery of software-defined networks of creating overlays. And what we mean by an overlay is simply we take our network as is, and we create an abstraction of that network where we're going to have a control plane that gets us basic connectivity amongst all our nodes. But we're not going to include in that control plane the connectivity of the endpoints. We're going to abstract that, and we're going to move it to an overlay tier, and we're going to create a virtual network on that overlay tier. So that underlay is simply serving as transport between the endpoints of the overlay. And it uses a control plane that is well understood, right? This is what we do for IP routing. Anybody in their right mind probably wouldn't create a layer 2 underlay to put an overlay on top of that. You just create a multi-pathed layer 3 network. So this is very well understood. Now, because we understand so well the underlay control planes, when it comes to the overlay, our natural tendency is, well, I have a tool that can actually give me some routing, so I'm going to try and use that in the overlay. And what I'm going to share with you is why that might not be the best approach. In any case, we create an abstracted network that has the sole goal of actually connecting the hosts to each other. And if you think about it, that's why we build a network. And that's where all of the services related to multicast, extranets, et cetera, are actually relevant. Now, if you think about this, all I have to do to get these nodes to talk to each other is map them to their connection point. Which switch are they connected to? And the mission of that overlay control plane is simply to serve as a directory or a mechanism to consult a directory where I keep those mappings of where the endpoints are attached. And by applying policy to this lookup of this database, I can create all sorts of features and functions that I need in this environment, including accessing things based on layer 2 addresses or IP addresses. So now I have L2 and L3 services. Well, I can color the routes and create VPNs without having to create a totally different address family. So all we're really doing is creating a directory of endpoints and how they can be reached in the network. And we're going to qualify that in different ways to create different features. So once I know where things are, the way I get between the endpoints is I simply encapsulate the traffic amongst the edge devices. Okay? So that's my overlay. When I look at the protocols that I can use, in the underlay, I use things like push protocols, like BGP, well-understood protocols. They distribute and push updates to all routers. You need them in all routers. You want them to be embedded in the infrastructure because you want fast convergence. You want a notification of a failure to be detected quickly, right? So very efficient in doing this. They're going to be calculating best paths consistently, right? Every time you get an update, you're going to process it. You're going to build a full graph of what you have and make a decision on how you keep routing. That is their goal. That's what they're good at doing, and they continue to do that. So they're ideal for the underlay. The underlay is relatively static. There's not a lot of mobility taking place there. So you can see how if I start trying to add mobility to this machine, I am going to be blasting the machine consistently, and I'm going to be driving the CPU use high, right? On the other hand, I have pull protocols. You could think of DNS as an example of a pull protocol. It's more of a transactional protocol. It's more of an environment where I only pull updates as I need them. And I am in no need of running path computation. All the resolution of multiple paths, loop prevention, et cetera, that's happening in the underlay, where I actually have multiple paths. In the overlay, I'm simply trying to get to the point of attachment. And in today's world, where you have virtualization and ways of clustering nodes together, there is no reason to have more than one point of attachment, at least not exposed to the overlay control plane, right? So we leave all that resiliency in the underlay, and we pull the functionality that's relevant to the endpoint to the overlay. So this is very dynamic, no path computation calculation, so I can move very, very quickly, and I can actually map and remap endpoints very, very, very easily. So how does it work? I'm showing a fabric here where my edge devices are basically V1 through V5 at the bottom, and I have a mapping system, which is a pair of nodes that are simply going to hold the mappings between the endpoints that are attaching to the system and where they are attached. We refer to those endpoints where things are attached, or to the nodes where things are attached, as tunnel routers. And we call them XTRs because we make a differentiation between whether we're using this to encapsulate or decapsulate the traffic. Those are also known as VTIPs in VXLAN world, right? And we will see how we can combine the VXLAN encapsulation with the LISP control plane. So what we do is very simple. The first thing that happens is as a host attaches, the host is going to register itself, or the attachment point is going to register that host with the mapping system. What goes in that registration is simply the address or identifier of the endpoint, which we refer to as EID, and the locator, which is usually the IP address of that attachment node. So when I register that, I start creating a database where I have the IP address or identifier of the endpoint, and what's the next hop, or which is the RLOC that it can be reached through. Notice I have added the virtual network identifier there. So if you think about it, all I'm doing is creating a mapping between endpoint and location. And I can add attributes to that endpoint or attributes to the location. In this example, I've added the attribute of the virtual network to the endpoint. So now the endpoint identifier is not just the IP address, but it's the virtual network, IP address. So that concatenation of information gives me the actual IP address of the endpoint. Now, if I'm going to implement a virtual network with this, all I'm really doing is mapping EIDs to RLOCs. I don't have a special address family to create a virtual network. right? And if that endpoint was was identified by a MAC address, I could create a layer 2 virtual network. And the registration and how I query the database would not change. It's all about identifiers to locators. So once I have registered these endpoints, and I'm only showing one for simplicity, but you can see how as many as I connect can be registered. Say the node on the right-hand side wants to get to host 1. Well, I send the packet. That packet actually is going to hit V5, and V5 doesn't have a route to this destination. So what happens is it triggers a lookup in the mapping system, just like you would in a DNS resolution. Okay, I want to get to cisco.com. I don't know the IP address. My IP address is actually the location. I resolve it with DNS. So I consult the mapping system. And one peculiarity of how we've implemented Lisp is that when I consult the mapping system, I can also subscribe to the information about that destination that I'm consulting. Okay, so say, where is IP1? And by the way, if anything changes after you notify me where IP1 is, do let me know. I'm interested, right? So that's the first thing that happens. I get a response from the mapping system that simply tells me, well, IP1 is on VTIP v1, okay, or XTR v1. Very simple, right? And that's it. That's the protocol. Now you can see here how I'm only getting updates for IP1 in v5, where I have interested endpoints. V4, V3, V2, there's no connection to IP1. Therefore, I have no use for that information. Okay? So the activity is scoped. And this is very important to scale and performance. The other thing is I'm not running any calculations. So because of the scoping of the activity, you could compare push protocols and pull protocols in similar loads across the network. And you will see that the pull protocol in our testing has resulted in about a 10% or less of CPU utilization. Meanwhile, the same load, similar activity, using something like BGP, we were basically pushing on 80%. Okay? So that's just a reference point in terms of how the CPU load compares. Now, once I get that response, I'm going to cache it in my hardware tables, and I do that so that I'm not doing a lookup for every single packet, right? So the next thing is, how do things move? So say I've got host 1 attached to VTIP 1. It moves to VTIP 3. And the only thing that happens now is I re-register it with the new information. Now, usually when you register things with the new information, you have to notify widely. So in our example, or in our case, we're only going to notify V1, or V5, sorry, which was where I subscribed. V5 was the one that had subscribed to IP1. And that's all I do for mobility. So you can see how this is very fast. Nothing is anchored anywhere. There is no home node or anything like that. Okay, no home agent. There's no anchoring of mobility. So it's actually direct mobility all the way to between the endpoints that are concerned with the connection. Okay. So how does that affect our performance? So if I think of a roaming environment as an environment where every host in average is taking a particular number of roams per minute, and I look at the number of endpoints, I'm going to see that there is a function of the number of endpoints and the amount of roams per minute or per second that are taking place, right? So what my control plane would see is the compound effect of all the nodes moving an X amount of times per minute. And that can get pretty high pretty quickly. So in an IoT example, we had a series of robots, and they moved about 20 times a minute. And you can see how that gives me about 5,000 roams per second, right? So now I'm bombarding a control plane with 5,000 roams per second. But the requirement was that the convergence was under 70 milliseconds for this. Right? So you have to process 5,000 updates in 70 milliseconds, or each one in 70 milliseconds, and they're all coming at the CPU. You know, they're staggered over that second for the most part, but it's still, we saw how the use of the control plane that didn't have to do the path computation and that had scoped updates was much more efficient in meeting these requirements than the push protocol. Very quickly, this is an environment that's supposed to grow to 100,000 robots, and you can see the rates of mobility that result from that in your slide. If I take a more conservative example, if I have a stadium where a lot of people are moving around, say you estimate about each person to move about one move from one VTEP to another about every minute, sorry. You got 60,000 people, your rate of mobility is still high, 1,000 roams per second. So the control plane gets hammered pretty hard. What happens in Lisp is, as I move, there's only a couple of nodes that get impacted. Okay. So now what I'm seeing is that my processing is much light on the XTRs. Right? So the XTRs aren't seeing 5,000 roams per second. The XTRs are seeing about 50 roams per second in that environment. If it's 100 XTRs, you roughly, right? It could be more, but it's not in the thousands, right? So the first thing is we're distributing the workload across the XTRs because the updates are scoped. The other element that's interesting is that I am able, because of the scoping of the updates, I am able to distribute the workload across the different control plane nodes, and I can do that efficiently. So if I was to think about the green robots being subnet 10 and the red robots being subnet 20, I can map subnet 10 activity to one mapping system and subnet 20 to a different mapping system. And I can actually horizontally scale my control plane. So the benchmark showed that for us to achieve 70 milliseconds or faster, we could handle up to 800 roams per second without any optimizations of the implementation of the protocol. Basically, we have a system where we can actually add control plane nodes and horizontally scale to keep the performance under 70 milliseconds and still handle as many endpoints as we may need. Okay.
That's a question.
Yes.
This is just considered totally arbitrary endpoints. But what if it's a group of servers who all of the time, providing a service, and therefore all the inputs will be subscribed. So that will be then considerably increment all these updates that, even though they're scoped, if it's a DNS service, a DHCP service, then how does it handle that? Because the load will be completely different.
Well, so then you're talking about an environment where you're actually seeing the mobility in one or two nodes, right? And we can still scope those.
Assuming it's one or two, it could be many, some kind of file or whatever. It's just was this tested in a different way, because it's not just about the endpoint subscribing to this device, but being this device one that it's providing a global service in a massive infrastructure. Then there will be a totally different load then.
Yes. So if everybody is subscribing to the service and the service is giving you these rates of mobility, then you have a problem of basically everything is getting updated at the same time, right? When we look at these IoT networks, et cetera, the controllers for these robots are in a specific place. The robots are the ones that are moving in general. The rates of mobility we found, and I've learned this from working a lot in the data center. We worked a lot on VM mobility, and now it's all the container moving, et cetera. What we found is that the patterns are much more predictable in the data center than they are outside of the data center. So usually where you have the move is on the different devices that are connecting, and then it is the servers that are actually more on the static side. But yeah, I mean, if you end up with the right mix, then you will actually burden the system in a way that is not
wondering, although in any case you will be able to share the load, but just wondering if it happens on a higher load, because this is what I see is that this is just driven, or at least thought to be applied on the access layer when you would see the real mobility. There are some places where it wouldn't move too much.
Right. And that's the logic of the testing, right? So then we contrasted that with the behavior on BGP. So we ran the test on both sides, and what we found was that in BGP, every time we had a move, we would advertise it, and it would be reflected to all the nodes. And then the node that where we departed from would actually get the advertisement and withdraw its route. And that withdrawal would also be flooded to all the nodes. So every time you got one of these updates, you would actually do a path computation. So this drove the CPU very, very high. And what we managed to do was we would get from one route reflector and one network, we would manage to get about 100 roams per second. Okay? So about 10 or 12% what we were getting out of a LISP mapping system, and this is a highly optimized route reflector. So the logic dictated, well, let's go ahead and scale horizontally and see if we can get around that problem, and maybe we just put bigger route reflectors, and that would be a solution. Now, the problem is that those updates are also being processed by the PEs, right? So as the PEs process these, they are a bottleneck just as much as the control plane node. So the fact that I don't have scoped updates actually got the best of this network, and we don't really have the option of scaling the control plane horizontally, right? So this would be a matter of vertical integration. I would have to put basically a very, very powerful route reflector in place to do this with BGP. So these are some of the things that we found in terms of performance and the ability to scale horizontally when we were using Lisp as a control plane for our access network fabric, right? So that was one of the things I wanted to share with you. The other thing was that we have all of these different protocols that we use today, and we're trying to consolidate it into fewer. So the first step is to use the overlay and drive L3 to the axis. That removes a lot of the first hop routing protocols or redundancy protocols. Or a lot of the L2 protocols, basically, those get set aside. You can do that with any overlay. Then there were a series of features like extranetting, multicast, the VPNs, etc., that did affect which protocols you use, right? If you look at the history of what we've done in the WAN, for example, you've got a stack of DMVPN and a series of other protocols to actually make that a reality. So we basically created a system where we can use the same principles of registration and request reply to create all of these features without really changing things. Now, the only thing that we would modify is the attributes that are associated with the EIDs and the RLOCs. And based on those attributes, then you can apply policy. So every single feature looks like an evaluation of attributes and policy at the time of doing a lookup. And the answer that I gave you would either put you through a service chain, put you in the right VPN, have you go across VPNs, make you forward in a multicast tree. So all of these things are now basically simmered down to using the same principles. So operationally, you're down to learning one principle. And then the rest is policy. For example, if I look at extranetting, traditionally, what I've done with extranet is I take, say I've got 3 nodes in those 3 boxes. I take all the routes from VRFB and import them into the extranet VRF. I take all the routes from VRFA and import them into the extranet VRF. So now the extranet VRF has its own routes plus the VRFA routes plus the VRFB routes. For this leaking to happen in most implementations, I have to have an instance of the other VRFs in there. And the export happens in the other direction, of course. So VRFB gets all the extranet routes plus its own. So you can see the number of routes that I've replicated inside that box grows very quickly, right? If I do things on demand, and it's just a policy that indicates when I hop from one VRF to another, I don't have to replicate any of these routes. So let's see how that works. Remember, we're saying that it's just a table of host to location, right? That's my fundamental element. And then I am going to add some policies. So here's an example of a policy that could be used. I am saying that IID1 or VPN1 can communicate with VPNs 2 and 3, and 2 and 3 can communicate with 1, but 2 cannot talk to 3. It's just a typical many to 1 and that 1 to many, but don't let them talk to each other. Right? So what we've done here is that my table of mappings remains the same as it would if I hadn't created the extranet. I'm not going to import things between VRFs. IID1 indicates VRF1. You can see how it's just the caller of the prefix. In this case, it's a host level prefix for host 1 and for host 2. And what I do is very simple. I go ahead and do a lookup where host 2 wants to talk to host 1. So I go ahead, do a lookup, map request for host 1. Since host 2 is in VRF2, the request comes in the VRF2 context, right? Well, my first operation is to look in VRF2. I'm going to look in VRF2, and I see that it's not in VRF2. So my policy says, well, you need to expand your lookup beyond VRF2 into VRF1, right? So I go ahead, look in VRF1, and I get a match, and I respond. When I reply with the location, but I also reply with the destination VRF that you should be in. And the only reason I reply is because my policy allows this. If my policy didn't allow it, say I consult VRF2 for something that is in VRF3, I would get a response that says, no, drop the traffic or redirect it to an intrusion prevention system. There's all sorts of measures you can take, right? That's all part of the policy that you can write. Now you can see how the mechanics here have not changed at all. I'm simply replying with information on how do I reach that destination. And all I'm saying is send it to edge node 1 and send it in VRF1, which is basically just your header identifier. Okay? So now I'm encapsulating to my destination in ID1. I'm going across VRFs, and I'm not creating any additional state in the routers. Okay? That's one example. Another example is multicasting. So imagine a world where my listeners send IGMP reports. When they say send IGMP reports, that triggers the registration of those different VTIP or these XDRs as listeners of that multicast group. So what's happened here is that those two listeners have triggered the registration of V4 and V5 as locators for a particular multicast group. And I called it L here. Not sure why. I guess for listeners. But you get the idea. So I'm receiving a report for 225.0.0.1, for example. And I'm going to register that 225.0.0.1. And I'm going to start aggregating all the registrations that I receive. And I'm going to create a replication list. In addition, I can have intermediate routers register themselves as replicators. And I can combine that into my list here. And I can basically create a mapping, a destination of RLOCs that can be used for me to handle multicast.
It means that all the RLOCs are basically doing something analogous to an RP.
Not all. So this would be an analogy to an RP, this VA, this intermediate tier. You can opt into that or not, but yes, that's a good analogy to think about the role there. So without doing anything special, you can have the replication happen at the head end and send everything to V4, V5, and you send individual copies. If not, you can send a single copy to something that is topologically reasonable. In this case, it would be the spine. The key is that I am going to do a lookup for a multicast destination, and I'm going to get a reply of RLOCs.
It will always be based on that.
Yes. Yeah. And in that way, if I move my source, I don't have to recreate my trees, right?
No, you'll be just an interest listen, and it may be another repeat or another RLOC.
Correct. Correct. So it's the same principle for multicast. And I can do the same thing for service insertion. So now I can have my controller determine, okay, this is the service chain that you should follow, and that policy is written into the mapping system as basically a chain of RLOCs. And I'm going to go ahead and at V1, I'm going to go consult for destination. It's going to tell me send it to V3. And then I get to V3, and V3 consults again, and it's going to tell me now send it to V5, and I'm completing my service chain.
So is it simply a rewrite, or it's possible to just get an ordered list of hops, like in source routing, in which I tell you that it would be strict or loose and go here or there, or you just simply will rewrite it? Or?
There's two implementations. One in which you have you download the entire string,
Okay.
and then you know where in the string you are as an endpoint. And the other one is one where you consult. The string exists in the mapping system, and you consult at every node. Okay. So you have those two options, and those were just some examples. I can integrate policy into this, where I can say, if I am requesting from V1, and you're asking for something that is mail, I will send you through a firewall or some device. If you're asking from V2 and it's mail, I'll send you directly, because I trust people in V2, but I don't trust people in V1.
It's analogous to the extranet, because you will anyway have the context aware, so you
got it.
top the other one.
You got it. So it all works the same way, and you got all these features, and you can extend it as much as you need to. Right? We have derivation of group tags that can be put into this. I can actually download my group tag at source, and now I can enforce group policies at ingress.
And the EID.
Mm-hmm. Yep. So very powerful, and I went over my time, but in summary, we have some clear scale benefits, some very interesting performance. We think we've simplified things because it's one set of operations, and it's very extensible. I mean, there are things coming down the pipeline like distributed NAT that would be of much interest in all the campus environments that we're working on. So.